Hello, students. So today's topic of discussion is mole concept and Avogadro number. So what is mole? Let's first understand what is mole. Mole is nothing. It's just a big number. It is like 6022 followed by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So can you imagine how big a number is this? And it's very difficult to, write this big number every time. So it was written as 6.022 into 10 to the power 23. Still, it's quite bigger number, when we're writing as 6.022 into 10 to the power 23. Hence, this was given a name called mole. Because you don't have any mathematical system to read out such a big number. So instead, we started calling it as mole. And this number is called as Avogadro's number. Now, the question might come to your mind that why do we use such a big number in chemistry? I mean, in your everyday life, you never use this number. I mean, let's talk about money. Anybody in this universe will not have this much amount of money either. So, why in chemistry are we dealing with such a big number? What is the use? What is the application? So, in chemistry, what is going to happen is the types of particles that you come across, the two broad types of particles that you will come across will be atoms and molecules. There will be other particles too, like ions and everything, but I'm again saying as this is the two broad categories that we are going to deal in chemistry. Either we are going to deal in atoms or we are going to deal in molecules. And these atoms and molecules are so small, I mean, they are not visible to the naked eye. If somebody is trying to view these atoms and molecules individually, like suppose if I want to see two atoms of oxygen, I will not be able to see that. If I want to see two molecules of water, with the naked eye, I definitely will not be able to see that. But when it comes to looking at water inside a glass. Suppose I have a glass of water over here. This is H2O. If I try looking at the water inside the glass, it is clearly visible, isn't it? So the question comes when we deal at a very small level, like if I want to see two molecules, three molecules, four molecules of water, I am unable to see that with the naked eye. But when I have a glass of water, then I can clearly see water inside it. It's simply because water has been taken in terms of moles inside this. So the amount of water one has actually taken is a multiple of this number inside the glass of water. Hence, you are able to see water inside the glass. Had it been only one or two or three molecules, you would not have been able to see with the naked eye. But since it is a multiple of such a big number, which is called the Avogadro's number, so that is why in chemistry, the importance of moles comes into existence, that to be able to see the atoms and molecules, you will have to take them in the multiples of Avogadro number, or simply saying you will have to take in terms of multiples of mole. So remember, mole is nothing. It is just a number. Mole is just a number. Let me repeat it for you. Like, for example, one dozen. Dozen is a number, right? Dozen represents 12. Century represents 100. Similarly, whenever we talk about mole, mole represents 6.022 into 10 to the power 23. Okay, moving ahead with the discussion. So, as I said, to be able to see atoms and molecules in chemistry, you will have to take them in multiples of mole, that is Avogadro's number, 6.022 into 10 to the power 23. Now, making you understand, suppose the tip number one that is going to help you in stoichiometry is that stoichiometry is nothing but it's kind of a unitary method that you deal in mathematics. In your junior classes, you must have learned how to calculate. Suppose if it says that cost of 5 mangoes is rupees 150. So what will be the cost of 2 mangoes? What will be the cost of 2 mangoes? So here, unitary method comes into play, and the unitary method that I am going to tell you in this chapter will help you solve toughest questions in this chapter without using any formula. Otherwise, in all the books and n number of places you will come across, they will tell you formulas of moles and how to calculate all that. I'll try to make it simple for you, like what happens in unitary method. Here we were dealing in mangoes and the cost, right? The two things that was being dealt with. So in your rough column or in your head somewhere, if you want to do it mentally, just make two columns, mangoes and cost. What was given to you in the question? If mangoes were 5, the cost was rupees 150, right? And what did they ask you for? That the number of mangoes, if it is 2, what is the total cost? So obviously you are going to assume it as X. So now in your head, what you just need to simply do is just cross multiply. So here 5 times of X is equals to 150 times of 2. So X comes out to be 150 into 2 divided by 5. 30. This gives you rupees 60 as your answer. This is what you have to do in the entire stoichiometry. You have to apply this one method called the unitary method. And my tip number one that I was supposed to tell you is that calculation, remember, calculation remains the same at microscopic and macroscopic level. Now, what do I mean by microscopic and macroscopic level? See, as I was discussing about water molecules earlier. So let's take water as an example again, H2O molecules. So if I take 5 molecules of water, As I told you, molecules are very, very, very small in size. Taking 1, 2, 3, 4, 5, 10, 100,000 molecules will not make them visible to the naked eye. You will not be able to see these five molecules. Whereas, on the other hand, if I take 5 mole molecule, then definitely I will be able to see them. So when we are dealing in 5 molecules, 10 molecules like this, 100 molecules, which we obviously can't see through the naked eye, this we term it as microscopic level. This is a simple terminology just used by me to make things easier for you to understand. So, and this is macroscopic level, taking large amount of water. Now, so as I explained you over here, if you look at this point, I said that the calculation remains the same at microscopic and macroscopic level. Now I will try to make you understand the concept. Okay, so for that, first we need to understand about the mass. So again, taking water molecule as the example, you know that one molecule of water. So now you know that this one molecule of water obviously will not be visible to the naked eye. If I try to figure out the mass of one molecule of water, can you suggest me what unit would you want to work in? Because one molecule of water is not visible to you. Let's talk about a grain of rice. A grain of rice, this I've drawn for you, grain of rice. It is visible to you, right? You can clearly see with the naked eye. The mass of this grain of rice will also be in certain micrograms. That is 10 to the power negative of 6 grams. Just giving you a rough idea. I'm not saying that it is going to be exactly micrograms, just giving you a rough idea of how things are dealt in chemistry. So this mass of rice would be in some multiples of micrograms or something like that. But the condition is that this grain of rice is clearly visible to you, right? Now, but when we're talking about molecule of water, it is not visible to us. So definitely the mass of one molecule of water would be even smaller to be not be able to measured in micrograms. So whenever we are dealing in such small species whose mass is like very 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 small, so the unit used in chemistry is atomic mass unit, also called as AMU. Even further simplified version is U. So whenever we are talking about one molecule, two molecules, 10 molecules, and we are trying to calculate the mass of that, so it is suggested that you deal in U. And if you start taking the molecules in bulk, bulk in chemistry means mole. So if I write mass of 1 mole of water molecules, then the mass that we are going to deal is in grams. And the best part that I'm trying to tell you over here is that whatever mass of one molecule of water will be numerically, the same will be the mass of 1 mole of water. Numerically, it is only the unit that is going to change. And hence I wrote that calculation remains the same if you're dealing at microscopic level or macroscopic level. Because at times it becomes difficult for you guys to imagine things in moles. It's all right, it's absolutely all right. You can imagine in terms of atoms or molecules. Do the calculation in terms of that. And when you realize that the question is dealing in bulk, question is dealing in moles, just change the unit of your calculations. That's it. Otherwise, the numerical calculation remains the same. This is tip number one, tip and trick number one for this chapter, stoichiometry. If you want to do formula-less stoichiometry, you want to apply some common sense and solve questions, you need to follow these tips and tricks. So remember that the calculation remains the same. So I'll just show you a demonstration over here by taking an example. So atomic mass of hydrogen, or to be very precise, relative atomic mass. So these atomic masses and all are calculated relatively. This we'll discuss in another video separately. What is the understanding behind the term relative? But I'm just telling you that relative atomic mass of hydrogen atom. So atomic mass, as the term suggests, it's the mass of one atom. Hence the term atomic mass, mass of one atom. And as we have been constantly focusing on this concept that this one atom is not going to be visible to me, so obviously I am going to deal in the unit of mass as U and not grams, milligrams, or something like that. I'm going to deal in U. So mass of one atom of hydrogen, relative atomic mass of one hydrogen atom is 1 U. As of now, you can take it as a fact. And as I said, I'll be discussing the term relative in another video, how and why we take relative masses in chemistry. Okay, similarly, relative atomic mass of oxygen, that is mass of one atom of oxygen, is 16 U. Now let's apply some mathematics. So if somebody asks me molecular mass of water, so now molecular mass means what? So atomic mass meant mass of one atom. Similarly, molecular mass means mass of one molecule. And again, this one molecule is not going to be visible to you. So obviously you will prefer calculating the mass of one molecule of water in terms of U, AMU. So now we know that water molecule is made up of two hydrogen atoms. So 2 into 1, because mass of one hydrogen atom was 1 U. And there are two hydrogen atoms here. So 2 into 1. There is one oxygen atom, and mass of that oxygen atom is 16 U. So if I do this calculation, 2 times 1 U and 1 times of 16 U, the calculation comes out to be 18 U. So this term over here, mass of one molecule, as I was discussing in chemistry, that is called as, the terminology given to you is molecular mass. That is mass of one molecule. Now, again, coming back to the discussion, I was trying to prove you that the calculation remains the same. I was trying to show you Rather, I should say that. So over here, now if I change my terminology and I say molar mass of water, molar mass of water. So as the term molar mass suggests, molar mass is mass of 1 mole of the substance, mass of 1 mole. That means 6.022 into 10 to the power 23 molecules. So obviously you've taken a lot of water molecules and they are going to be visible to the naked eye. So the best part that I was talking about, that the calculation remains the same. So over here, the mass will still come out to be 18. So whether it is one molecule or it is 1 mole, the numerical calculation remains the same. The only thing that changes is 18 grams, the mass, the unit, rather, I should say. It is the unit that changes, rest everything remains the same. The numerical calculation remains the same. So if you keep this thing in your mind that calculation is going to be the same whether you deal in microscopic level or macroscopic level, trust me, you will not be needing any formulas while solving questions of this chapter. I'll give you another example. Suppose I take carbon dioxide molecule. So this molecule is made up of one carbon atom and two oxygen atoms, right? And that's what a molecule is. It's a combination of atoms. So I have one carbon atom and I have two oxygen atoms. So if I take 5 molecules of carbon dioxide, tell me something, that is it going to be visible to the naked eye? The answer is no, because we are dealing at a very microscopic level. We have only taken 5 molecules. So obviously, when we are trying to calculate mass of 5 molecules of CO2, so it will be 5 times mass of one molecule. That's pure mathematics. Mass of one molecule of CO2. And how do we calculate mass of one molecule of CO2? It's very simple. You need individual atomic masses. So atomic mass of carbon is 12 U, and atomic mass of oxygen is. You can easily refer to the periodic table, but these are certain basic elements that you will come across every now and then. So gradually you will also learn the values. Automatically you will learn it. You don't have to put in some extra efforts to learn the values. Sorry, atomic mass of my bad. Atomic mass of oxygen is 16 U. Just because of that water thingy that we have been constantly discussing, I just wrote it as 18. Anyways, so how do we calculate mass of one molecule of CO2? So there is one carbon atom, so 12 into 1, plus there are two oxygen atoms, so 2 into 16. So this comes out to be 5 into, solving this part gives you the value as 44. So 5 into 44, 5 fours are 20, 4s are 20, 220 U, because we are dealing only in 5 molecules. And had the scenario been, instead of 5 molecules, had the scenario been mass of 5 moles of CO2. Now, simply, you don't have to get worried or panic in the paper or in the after looking at the question. You just have to understand that now you are taking a lot of CO2 molecules. And I said at microscopic level, you were dealing in five molecules. At macroscopic level, you are dealing with 5 moles. So final answer, final calculation will still come out to be 220. It is just that the unit is going to change, and that is grams. So only thing you need to be careful about is to understand if you are dealing in microscopic level in the question or you are dealing at the macroscopic level. Accordingly, you will have to adjust your units. So for atomic mass and molecular mass, that means mass of one atom and mass of one molecule respectively, since they are not going to be visible to you. So with the naked eye, obviously. So the unit taken is U. And if you're dealing in 1 mole of atoms or 1 mole of molecules, which is called the molar mass. So over here, when we were writing the notes, I will just use the terminology molar mass over here. So when you are taking 1 mole of any substance, the mass actually becomes the molar mass. And if you take mass of one molecule or one atom, it becomes molecular mass or atomic mass. But again, what is important is this tip and trick number one, which tells you that calculation remains the same at microscopic and macroscopic level. So initially, since you guys have just started with stoichiometry, so it becomes very difficult to imagine things in terms of moles. It's absolutely all right if in the question they are saying 10 moles of certain molecules, don't imagine as 10 moles. Take it as 10 molecules. Do the calculation as per 10 molecules and then come back to the reality because it is actually dealing in moles. So just change the unit of your calculations. Rest, everything remains the same. Tip and trick number two. With that trick, we are going to finish the lesson for today and we are going to practice certain questions after this. So your tip and trick number two, you always know how to calculate or how to do calculation for one. Remember this tip and trick. So first tip and trick was the calculation remains the same at the microscopic and the macroscopic level. And the second tip and trick, which is going to help you in this chapter and make this chapter formula-less for you, is that you know how to do calculation for one atom, one molecule, 1 mole. You will always know how to calculate things for one. This is going to act as a very, very important resource for you in any tricky question. If you're stuck, remember that you always know how to do calculations for one atom or molecule or 1 mole of any substance. So for one, you know how to calculate. Like for 1 molecule of water, I know how to do the calculation of mass, right? I did it over here, mass of one molecule. This data I'll get from the periodic table straight away, and I can do the calculation. That becomes a very, very important resource that I know how to calculate things for one. All right. So let's do some questions together. Let me make you understand how to deal with things in stoichiometry. Okay. So here is the sheet for you. I'll solve certain questions for you. You just take down the notes thoroughly, and if you want to write it. Otherwise, the notes will be available to you in the link. Okay, so let's deal with this first question, A part. It says calculate the number of moles in 54 grams of water. So now again connecting the dots and connecting whatever we have learned. So how much water have I taken in this question? 54 grams of water. Now, as a chemist, you have to understand that 54 grams of water is a lot of water. You are dealing at a macroscopic level. In your head, you have to understand this. For a common man, for a common human being, everyday life, 54 grams is nothing. It's a very small value. But since you are dealing in a subject called chemistry, where molecules and atoms are very, very, very small, so 54 gram technically means you have taken a lot of molecules of water, right? So again, now the two things that are being dealt over here is number of moles and mass. So as I said in the lectures in the beginning that you have to apply unitary method. So one thing that is being dealt is mass of water, and the other thing that is being dealt is number of moles of water, right? These are the two things that are being dealt in the question. So what is the mass of water molecules given to you in the question? It is 54 grams, right? And hence we are dealing in moles because it is dealing in grams. And it is asking for the number of moles. So let us say this is X, because whenever we are dealing in moles, the mass is going to come in grams. Here comes the application of tip and trick number two, which says that you always know how to calculate mass for one. So if I have 1 mole of water, H2O, if I have 1 mole of water, so I know at the back of my head that I can easily calculate mass of 1 mole of water. And now connecting it with tip and trick number one, that calculation at microscopic level and macroscopic level remains the same. So instead of imagining it as 1 mole of water in my head, at the learning stage, obviously, I can take it as 1 molecule of water. Not a problem because my numerical calculation is going to be the same. So let me first calculate mass of 1 molecule of water. So for your assistance, the individual atomic masses are given. So you don't have to look at the periodic table now. It has been already given in the sheet. So mass of 1 molecule of water. So 1 into 2 because there are 2 hydrogen atoms. And then 16 into 1 because there is 1 oxygen atom. So mass comes out to be 18 U because I'm talking for 1 molecule. And now I will have to change my interpretation from 1 molecule to 1 mole because question was dealing in moles. So unfortunately, we'll have to change our understanding from molecules to moles. So mass of 1 mole of water, as discussed, the numerical calculation remains the same. Only the unit will change. So it is 18G. And that's what I have to write over here, 18G. So my tip and trick number two, that I know how to calculate things for one. So I have calculated for one. So mass of 1 mole of water is coming out to be 18G. And as per unitary method, I have to calculate that 54 grams has how many moles? So simply cross multiply. That's how you apply the unitary method. So 18 into X is equals to 54 into 1, and on solving this, X comes out to be 54 by 18, that is 3 moles. So my final answer to this question would be 3 moles of water. So, all right, now you understand that 54 grams of water, because it was 54 grams, so it has to be a lot of water molecules as per a chemist. And the answer was coming out to be 3 moles. Now, in your textbooks, there is a formula that is given to calculate the number of moles. And that formula is, I'll just show you what that formula is. But I personally feel that solving the questions with a unitary method and applying the tips and tricks that I've told you is going to make you understand chemistry better rather than, making it a formula based thing. It is going to make you understand chemistry better. You are going to imagine things in a better way. So, my personal suggestion is to apply some common sense. But if you want to use the formula, so the formula given in the book says number of moles is denoted as N. So number of moles of any substance is given mass upon molar mass of 1 mole of that substance. Although the amount of calculation is going to remain the same only. So given mass over here was 54 grams. Right. And molar mass, as I've been telling you, molar mass means mass of 1 mole of the substance. And that's what was my tip and trick number 2, which said that you always know how to calculate mass of 1 mole. So again, if I calculate mass of 1 mole of water, in my head, I'll do it mass of 1 molecule of water. So it will come out to be 18. Since it's 1 mole, so the mass becomes 18 grams. And if I solve it like this over here, it is still going to give me 3 moles. So at the end, it totally depends on you. You want to use the formula or you want to use the tip and tricks and the understanding of chemistry. That's up to you, totally up to you. You will get answer in any case. Got it? All right. Now coming to question number 1, part B. The question number part B, 1B says that you have H2O2. Now you know H2O2 is a molecule. It's a combination of atoms. There are 2 hydrogen atoms and there are 2 oxygen atoms. So it's combination of atoms. Hence, it's a molecule. And how much H2O2 have I taken? 6.8 grams. So again, as a chemist, you know 6.8 grams is a lot of H2O2. As a common man, this might be a very, very small amount, but 6.8 grams as a chemist is quite a lot of H2O2 molecules. So obviously you are going to deal in moles, and that's why the question was asking about number of moles. So again, tip and trick number 2, you always know this is the best resource that you have, that you always know how to calculate things for one. So let's calculate mass of one H2O2, one molecule, obviously. Mass of one molecule of H2O2. So it is going to be 1 into 2 plus 16 into 2 comes out to be 34. Since we are talking about one molecule, so it's 34U. But then I realized that question is playing in moles. So I'll change my interpretation to moles. So mass of 1 mole, or you can also call it molar mass of H2O2. Tip and trick number 1, the calculation remains the same. So 34 G is what now my interpretation would be. Molar mass of H2O2 is 34 G. Mass of 1 mole of H2O2 is 34 grams. So again, tabular way, unitary method, because I don't prefer using the formula, but you can absolutely use the formula, not a problem. And I'll show you how by using the formula also you can get the answer. So the two things that were being dealt were mass of H2O2 and moles of H2O2. So mass given to me in the question was 6.8 grams, right? And moles of H2O2 I had to calculate. So it's X. For one, I have already done the calculation. So if I have 1 mole of H2O2, the mass would be 34 grams. So if I cross multiply, so I'll get the value of X as 6.8 divided by 34, which is nothing. As per the formula, this is your given mass. So if anybody wants to apply the formula, that is also fine. But personally, I suggest that to go into the depth of chemistry, you need to imagine things, one molecule, 1 mole, and do that calculation unitary method wise. So it's one and the same thing. And this is your molar mass. So the answer will come out to be the same. It's 0.2 moles will be my answer to this question. All right, let's move to the next question. Question number 2. Calculate the mass of 3 moles of carbon dioxide. So again, very simple, and the individual masses have been given to you. So mass of one, I always know this is the best resource, so I can calculate mass of one molecule of CO2. I can always calculate this in my head. So that's 12 into 1 plus 16 into 2 gives me 44. Then I see, oh, it's one molecule only, so I take it as 44U. Then I realize that the question is playing in moles. So mass of 1 mole of CO2. So tip and trick number 1, that the calculation remains the same. So since it is 1 mole, earlier it was one molecule, 44U, 1 mole will be 44G. And now simple unitary method, they're asking for 3 moles. So mass for 1 mole, I know. 1 mole is 44. So mass of 3 moles, simple mathematics, would be 44 into 3. And that calculation, sorry, that calculation is going to give me 44 into 3 will give me 132 grams, because I'm dealing in moles, I'm dealing in bulk, I'm dealing in a lot of molecules. So answer will come out to be 132 grams. And if somebody is interested in applying the formula, so over here also I'll help you looking at the formula. Number of moles is given mass upon molar mass. The number of moles was given to you in the question 3. Given mass you were supposed to calculate because you didn't know the mass. And molar mass you have just calculated over here, it is 44 grams. So from here also obviously you will get the same answer. 44 goes here, multiplied by 3 gives you the given mass. So again, the choice is open to you. You want to use the formula, you can use that. You want to use common sense, unitary method, tips and tricks, you can use that too. So similarly, now I'm sure you'll be able to do question number 2, B part. I'm sharing the answers with you so that you can cross check and verify. So mass of 4 moles of carbon monoxide, CO, will be 4 times mass of 1 mole. Mass of 1 mole you can easily calculate, 12 plus 16, that is 28. So answer will come out to be 112 grams. Not you. 112 grams because you were dealing in mole. For the C part, I think I should discuss this with you rather than giving you the answer directly because this is a different question. But let's discuss first. Okay. So they're asking us to calculate mass of two molecules of carbon dioxide. Again, applying tips and tricks. Mass of one, I always know how to calculate. So mass of one carbon dioxide, you will do 12 into 1 plus 16 into 2 gives you 44. Since you were calculating for one molecule, so it becomes 44U. The question is not talking about moles, so I am not going to convert this mass into G. I am not going to convert this mass into G over here. I'll keep it as U only because the question is not dealing in moles. And the question was asking about mass of two molecules. So two molecules will be 2 into 44 because one was 44. And since it's only molecules which are not going to be visible to me, so the unit remains the same 88 U. So I will not play in grams in this part of the question because question was not dealing in modes. Very quickly, let's discuss question number 3 as well and then 4. So question number 3 is asking which has higher mass, 5 moles of water or 2.5 moles of carbon dioxide. Very simple. You know how to calculate things for one. So let's mass of 1 mole of water. Now, since you have done this calculation many a times, I'll simply show you mass of 1 mole of water is 18 grams. That's the molar mass. And the question was talking about 5 moles of water. So mass of 5 moles of water is 5 into 18. That is 90 grams. Similarly, on the left side, I'm going to do the calculations for carbon dioxide. So mass of 1 mole of, again, that calculation I've done n number of times in this video. So mass of 1 mole of carbon dioxide will be 44 grams and mass of 2.5 moles of CO2 would be 44 into 2.5. Whatever that calculation comes out to be, I think that is going to come out to be 44 into 20.5 would be 88 plus 22, 110 grams. So now you just have to compare which has more mass. See, in terms of molecules, water was 5 moles. You had a lot of water molecules compared to carbon dioxide. But we were not supposed to compare the number of molecules. We were supposed to compare their masses. And as per calculation, I can see that 2.5 moles of carbon dioxide has more mass, has higher mass. Coming to the last question, and this will finish our lecture number 1. I hope the concepts were clear to you. In case of any doubts, I'll be hosting my live sessions. You can anytime come in those live sessions and ask your doubts. Those sessions would basically will be for your doubt discussions only. So if mass of 10 molecules of NH3 is 170 U, see first understand that if the data given is proper or not. I technically see that it is dealing in molecules, not in moles. So the unit should be U and it is U. So that's absolutely correct. So they're asking me what is the molar mass of 1 mole. And over here, if you can see, they have not given you the individual masses. Why? Because it is not needed over here. They had given you mass. So again, simply, I believe in unitary method, so I'm applying that. So mass of NH3, they had given it to you, and they had given it to you number of molecules. So number of molecules. So mass of NH3 that they had given you was 170 U. Number of molecules was 10. And as I have been laying emphasis that mass for one you can always calculate. So over here also I'll calculate mass of one molecule. It is, let's say, X. So cross multiply. It comes out to be 10 times of X is equals to 170. So X comes out to be 17 U. This is mass of one molecule. So now I know in my head that mass of one molecule. So now I don't need those individual atomic masses. So mass of one molecule is of NH3. From my calculation, I got to know I did not need any individual masses, atomic masses over here. The mass of one molecule of NH3 is 17 U. And the question was about molar mass, that means mass of one mole. So tip and trick number one, that calculation remains the same. So if it is mass of one mole of NH3, the mathematical value will still be 17, but the unit will straight away change from U to gram. So this is my final answer. Mass of 1 mole, that is the molar mass of NH3, is 17 grams. That was it for lecture number 1. In the next class, we are going to we are going to learn how to calculate empirical formula, and thereafter we are also going to understand how to apply this mole concept to chemical reaction. So that's it for today in the video. Thank you.